we're now in section 4.3. What 4.3 is all about is the derivative of e to the x. The first thing we want to note is what delta x is going to be under the limit. So what I mean
What slideshow is this?
the limit.
What slideshow is this?
Say what?
What slideshow is this? Like, what's it under? For the notes.
Oh, I haven't posted them yet.
Okay.
You're gonna have to flip between those screens. You should be able to add a pin and see what's on the blackboard. I mean, what's on the projector while I work on the blackboard at the same time.
Okay.
Should be able to. But anyhow, so the first thing we're gonna need to do before we can actually find the derivative of e to the x is observe that 1 plus delta x raised to the 1 over delta x. The limit as delta x goes to 0, this thing's going to just be e. Just like it was when it was x that we had in here, right? And nothing's going to change here. The second thing we're going to need to notice is that the limit as delta x goes to 0 of delta x, this thing is dx, right? We said it's about 0, but it's not exactly 0, right? Just like that. So, that tells us then that this is going to be the case, right? That the limit as delta x goes to 0 of e to the delta x, it's pretty damn close to e to the 0. It's like that, is what we're saying, right? And this, let me actually write it like this. So it's e to the 0, and this is 1, right? So for really small delta x's, this is about 1 plus delta x. Does that make sense what I mean? Kind of, sort of? All right, so having said all of this, find the derivative of f of x equal to e to the x. We're going to do everything the same way pretty much. We just need to make note of those two things. So we got the limit as delta x goes to 0 of f of x plus delta x minus f of x all over delta x that's going to be the limit as delta x goes to 0 of e the x plus delta x minus e to the x all over delta x but this is going to be like the limit as delta x goes to 0 of e to the x times e to the delta x minus e to the x all over delta x. We can factor out that e to the x now. We're going to get e to the x times the quantity e to the delta x minus 1 all over delta x. Well, we just saw a minute ago that this thing is like 1 plus delta x. So we have the limit as delta x goes to 0 of e to the x, that quantity times 1 plus delta x minus 1 all over delta x. We're going to have some cancellations in here, right? This one and this one's going to cancel. So we're going to be left with then the limit as delta x goes to 0 of e to the x times delta x over delta x, where, well, our delta x's are going to cancel. What we're going to be left with the limit delta x goes to 0 of e to the x, which is equal to just e to the x. So d dx of our function is equal to e to the x. In other words, the derivative of e to the x is itself. I did not just almost slip and fall on a cord. Having said that, this is a very particular solution, right? By some of our past rules, we know that if our function is actually e to some function of x, right? Then the derivative of this thing is going to be e that function times the derivative of that function. Everybody cool with this? In other words, one interpretation of this result is that for any given point along e to the x, so for any y value of e to the x, that's equal to the slope of the tangent line at that same point. So let's say we have some random point here. And we want to know what the slope of the tangent line was to that point. Well, we know the slope of the tangent line is equal to the derivative of our function, right? And in this case, that happens to come out to be the point in question, the y value of that point in question. Make sense? Is everybody cool with this? So before I had asked y'all to check out or to consider what might make E so special. Why is it we might care about it? This is why. The fact that this happens makes it a great tool for us. Is everybody cool with this? So having said that, as a couple examples, let's consider we have the function. We're going to have a couple cases up here. F of x is equal to e to the negative 3x squared. Let's consider c as well. G of x is equal to 6e to the x cubed. All right, we're going to consider these two cases here. Well, we know that d dx of e some function is equal to e to that function times the derivative of that function, right? So because of this, given that f of x is equal to e to the negative 3x squared, identifying what u is, u is equal to negative 3x squared, right? So the derivative of our function here should come out to be e to the negative 3x squared times negative 6x. Everybody agree with this? All I did was find the derivative of this thing and multiplied by it, right? And comparing comes out to be the same thing. We found the exact same thing. So let's consider the other example now. C, where g of x is equal to g of x is equal to 6e to the x cubed. Our u to the x here, or u of the x, u of x is what I'm trying to say. It's it's going to be x cubed. So the derivative of g to the x, or g of the x, of x, it's going to be a rough day for me, I can tell it already. This thing's going to come out to be 6 e to the x cubed times the derivative of u of x, which is going to be 3x squared. Reducing all of this, we're going to get 18x squared times e to the x cubed. Comparing answers, same exact thing. Yeah? Having said that, I would like for y'all to do A, and I'm going to do C and B up here. So I would like for y'all at home to do A, and y'all were in the class, and I'm going to do these other two. So who's done with A? Folks at home, anybody done with A yet? So I'm going to take the silence to be no. The way we're going to go about A is just going to apply the product rule, right? You're going to take the derivative of one multiplied by the other, plus the one times the derivative of the other, right? Pretty straightforward. So really quickly looking at A, we're going to take equal to e to the x times the derivative of x plus x times the derivative of e to the x. So it's going to come out to be e to the x plus x e to the x. It's going to come out to be 1 plus x e to the x. Did everybody get that? So let's compare solutions then. Notice they didn't pull out the e to the x, but it's the same thing otherwise, right? Here, they pulled out the 1/2, the same, right? And here, same thing again. So these rules are still the same. Nothing really changes. We're just working with the derivative of e now. And it has a couple cool properties. That's really all we're trying to say here. Having said that, I'm going to let y'all work on this problem on your own for a couple minutes. Yeah, I'm going to give you all about 5 minutes to work on this problem. right, so far I've done the derivative. We're gonna have to find that at the very least, right? According to this problem, what we want to know is what the lowest point of the wire is. We want to show that it's midway in between the two, so we know 0, right? Like we for sure know that we're going to have x equal to 0. But how are we going to show it? Well, we take the derivative, set it equal to 0 to find the critical point, right? So taking the derivative and setting it equal to 0, we're going to get that 1/2 times e to the x over 60 minus e to the negative x over 60 is equal to 0. Multiply both sides by 2. When we do that, we're going to kill our 1/2, aren't we? Now we can add e to the x over 60, or my mistake, e to the negative x over 60 to both sides, right? Well, if this is the case, because the bases are the same, that must mean that x to this x over 60 and negative x over 60 are also equal. Does that make sense? Because both the bases are identical. If these two things are going to evaluate to be the same, then this has to be equal to this, right? Make sense? So we have that x over 60 is equal to negative x over 60, multiplying both sides by 60. We're going to get that x is equal to negative x, and that only happens when x is equal to 0, right? Make sense what I mean? So the answer to the question, where is our critical point? It's at x equal to 0, which would be midway, right? Okay. So from here, we want to know how far, how much does the wire sag. So what we're going to need to do is to find out what h at 0 is. Which I'm just going to go ahead and tell you is 60. Then we need to find out what h at 30 is, and h at negative 30, to make sure these heights are the same, or that we know which one is higher. And then take the difference between the highest value and 60. Make sense? So, to reiterate, this problem looks kind of like this, right? Here are these two power poles. They're spaced 30 feet apart. We've got this wire that sags. Just looking at this, we can see based on their axis, right, that this has to be at 60 feet. So doing the work, they went one step further here and added x to both sides, divided by 2, and said, hey, x has to be 0. Then they applied the derivative test, which I skipped because we knew from the setup of the problem that this was going to be a min, right? Like, realistically, we should have to do the first derivative test, but because of the way the problem was presented, we could just automatically assume it, right? Having said that, evaluating at 0, we get 60 feet. And on either side, they're the same height, and that's 67.7 feet. So the wire sags 7.7 feet. Everybody cool with this? Yeah. All right, so we're going to go about this problem. We got the demand function is equal to some exponential. We want to know what price will yield a maximum revenue. How are we going to go about this? Oh, my voice just croaked. What do y'all think? What's the function for revenue? It's the number of units sold times the price per unit, right? So we're told price is equal to 56 e to the negative. Where do they come up with these decimals? All right, 0.000. Is that 4 zeros or 3 zeros? 4. One, 2, x. And we know revenue is equal to x times price, or x times 56 e to the negative 0.000012 x. So looking at this, what do you think is going to yield a maximum revenue? You have to guess just from what you've seen up here. It's not obvious, right? Like, this is going to take some work. So the derivative of revenue is going to be (56 e to the negative 0.000012 x minus x times, I have no clue what that decimal is, times 56. So I'm just going to leave them. negative 0.000012 x, right? Now we're going to want to set that equal to 0 and solve. So revenue is equal to x times the price, right? Setting it equal to 0 to solve for x. And they're just making the point that it would actually be easier to use a graphical approach. The reason why they're saying that is because this is a lot easier to check out than working with those decimals. And that's all they're really trying to say. But if we were to work this out, we would get that x is equal to 83,300 units. Yep. Which makes sense because look at what's happening here. This is a really tiny decimal, right? Times an x value. So this thing is like 10, it's like 1.2 times 10 to the negative fifth times 0.83 10 to the fourth. So this thing's going to come out to be a small number, right? Makes sense what I'm trying to say? Having said that, I think that was the, oh, nope, I lied. It's not the last slide. All right, so we've all seen the bell curve. This is the function that forms the bell curve. This function has a bunch of particular properties that are really great for mathematicians and statisticians alike. But the point of what we're about to do now, what we're talking about here, is just that the bell curve is an example of an exponential function. So we want to show that this thing has inflection points at 1 and negative 1 in this first example. How are we going to go about that? What do you all think? The first or the second? The first derivative to find an inflection point? Should be the second, right? First derivative tells us mins and max. And then the second one tells us inflection points. So just to really quickly see what they're talking about, these are the points we're interested in. We can, just visually looking at it, see that they are in fact inflection points, right? So applying the first derivative, I'm going to get this thing. Applying the second derivative, after some simplification, we're going to get this. Well, notice, if we plug in -1 or 1, our exponential is non-zero, right? But x squared at 1 is 1. X squared at -1 is 1. minus 1, this is going to come out to be 0 in both cases. That's really all there is to this problem. But again, I just wanted you all to see what the actual bell curve function looks like. Because it is good to know where exponentials show up and why they're useful and why they're used. Having said that, now I'm out of slides. And we only have 5 minutes left, so I'm going to let you all go. But stick around if you all have any questions. It's all right. I'll just bill you later.